Hello everybody, I'm back with another video, and today I wanted to show you our latest discovery. I've prepared a little talk about it to show you what the problem is and how we solved it, and yeah, let's get right into it.
So here I'm back with my talk, and let's get right into it. It is said that when a student asked the famous physicist Werner Heisenberg how one could illustratively understand the hydrogen atom, he got the answer, "Don't even try." Obviously, this advice was taken too seriously, because even today, a truly understandable illustration of the thing we call atom is still not available. Admittedly, we have the orbitals of the electrons, and one can tell us that these are the probability fields of this particle, meaning where one can find it. But I have to admit that it doesn't really help me to understand this thing. On the other hand, it is not my style to accept an advice like "don't even try to understand this," and thus I will here try to give such an illustrative understanding. And why do I think that I can achieve what Heisenberg wouldn't even have tried? Well, I have something at hand which was not available to Werner Heisenberg: a geometric diversion of Schrödinger's famous equation, with which he had modeled the hydrogen atom almost 100 years ago. The one mathematical procedure, namely, which allows us to derive the general theory of relativity from Albert Einstein, is a perfectly rigorous manner, namely also gives, when just a bit generalized, all major quantum equations. And here it is, Schrödinger's great equation. I don't even try to explain the terms in there, especially as I don't understand them myself. But it is said that the triangle and the funny delta are operators. That's all we need to know. As the name says, namely, they do some operations to the function psi. Schrödinger had postulated this equation and published it together with the hydrogen application in two papers in 1926. As the equation is postulated, we don't really know why it gives us the result we see when observing the atom in reality, and this is the reason why Heisenberg struggled not to try to understand the thing in the first place. However, today a way was found to derive Schrödinger's equation from a fundamental geometrical principle, and this fact gives us the chance to finally understand atoms in a truly illustrative manner. It was shown by Norbert Schwarzer, who happens to be my father, by the way. The Schrödinger equation literally falls out of the geometric theory of Albert Einstein, the one theory we all know as the general theory of everything. Now, some of you may say, big deal, and how exactly shall this help us to understand the hydrogen atom after almost 100 years of don't tries? Well, as I said, the Einstein theory is geometric, and when we simply follow the path of how exactly the Schrödinger equation falls out of Einstein's great theory, we should also be able to geometrically understand the results the Schrödinger equation gives. My father's starting point was the so-called Einstein-Hilbert equation, a variational integral based on a Hamilton extremal principle. As I don't want to repeat his derivation, which is not only quite theoretical but also a bit boring, too many equations and almost no pictures, I here refer to two presentations where you can easily follow the calculation. The first presentation leads us to the Klein-Gordon equation, and the second one shows us how the Schrödinger equation can be obtained from there. The links are also given in the video description underneath the video. What my father obtained in the end was a completely geometrically based Schrödinger equation. Here, the first one on the slide. And now I think that when I'm moving along his geometrically derivation, one should be able to make out the true meaning of Schrödinger's result in an illustrative way, instead of some postulated probability pictures. Along the way, we have to adjust things like mass and potential, but how to do this was already shown in the book given in the bottom slide. The book is called The Math of Body, Soul and Universe. Here, the one important step for this, the one I made out as the one important one, is the thing my father did with the metric tensor. This tensor just describes our space-time in a compact mathematical form. My father simply introduced a factor he called metric scaling, even though one may better see it as a functional change of volume. This factor takes a certain form when we invert to derive the Schrödinger equation from the Einstein-Hilbert equation, and going with the derivation, we see, surprise, surprise, the Schrödinger solutions are only certain distributants of space-time. And with this connection, we found we can exactly illustrate now how a given Schrödinger solution or wave function is, as the physicists called them, changes the space and time. Here is just one example for the hydrogen solution of Schrödinger's equation of the letter gives us. Interestingly, we automatically have two ways in which we can insert the solution into our geometric picture, and one with a positive and one with a negative sign. I think that this has to do with the fact that so far we have not fixed the charges of our hydrogen atom. It could have a positive center and a negative periphery, or we could have it the other way around, like the antimatter hydrogen. You may ask now, where is the electron? Well, I could just answer anywhere, but please forgive me, this is the wrong question, because the Schrödinger model does not contain an electron. It solves the problem of an arbitrary something subjected to a central symmetric force field of the character 1 over r to the power 2. An electron, we mean a real one, was never introduced by Schrödinger. But having found the connection between the quantum equations and their geometric meaning, now we can refine the model to contain real particles. At least the big shorts in physics should be able to do this, and thus work us closer and closer to an illustrative understanding of the thing modern nature still hides from us and our understandings. To Werner Heisenberg, I would say, well, sir, I've tried, and I think I have found a way to understand the atom. In fact, I don't just understand it, I can even draw it and show it around. I can even put it into words and tell you that the atom is distorted space-time. And here I even go so far to suggest that the atom constituent parts, the elementary particles, are all just distorted space and time, and this one can show and even kind of understand. The distortion may be rather small, but it is there, and we realize it as the presence of atoms. With this fundamental connection being made, we have now the means to visualize the atom and its action in space and time. Well, that was my presentation. I hope you have all learned something, And yeah, I hope you have a great day, and until next time, I see you. Bye bye.